Hello everyone, welcome to the second of 4 videos looking at some past paper questions on the topic of orders of reaction and rate equations. In this question we've got some shorter answer questions compared to the longer one we looked at in the first video. This first one is asking us what is the overall order of reaction? And you can see that they've given us the rate equation here. This idea of the overall order of reaction is actually really straightforward. All we need to do is add up the orders of reaction for each individual reactant. So we can see from this rate equation that the I minus is second order because its concentration is to the power of 2. The IO3 minus is first order because it has no power here, so it's to the power of 1. And the H plus is second order again because again the concentration is to the power of 2. Now if something is 0 order, then it just won't appear in the rate equation at all. So this is definitely first order, not 0 order, even though there's no number here. And so then to work out the overall order of reaction, we just need to add up the orders for each of these. Okay, so the overall order of reaction is going to be 2 plus 1 plus 2. So the overall order of reaction is 5. Okay. Then in this question with the table, this is slightly different to what we've seen before. In the previous video, we looked at a question where you had a table full of data already filled in, and it was asking you to work out the orders of reaction and therefore the rate equation. And so this is essentially the opposite. We've already got the rate equation, and it's asking us if we make these changes to the concentrations, what effect would we expect that to have on the rate? So if we look then at what has actually changed here, if we compare the experiments, you can see that between experiment 1 and experiment 2, the concentration of the I minus has been multiplied by 3, and the IO3 minus hasn't changed, and the H plus also hasn't changed. Okay. So the only change we've got is with the I minus. If we look back to our rate equation, we can see that the I minus is second order. So therefore, if its concentration has been multiplied by 3, we would expect the rate to be multiplied by 3 squared. Okay, so therefore, we would get 0.6 times 3 squared. And we'd end up with a value of 5.4. If we then look at experiment number 3, I think the safest thing here is to compare this back to experiment 1, just in case we've got experiment 2 wrong. We know that experiment 1 is correct because it was done for us. So again, if we look at what's actually changed here, the I minus, its concentration has been multiplied by 4. If you can't see these just by looking at them, again, you can always just divide them on the calculator. Here with the IO3 minus, this has also been multiplied by 4. And with the H plus, this has also been multiplied by 4. Okay. So the concentration of each of the 3 reactants has been multiplied by 4. So we're going to expect a pretty significant effect on the rate here. You know, what's going to happen here? Well, with the I minus, we know it's second order. So we would expect that if its concentration has been multiplied by 4, we'd expect the rate to change by a factor of 4 squared. Okay. With the IO3 minus, it's first order. So if its concentration is multiplied by 4, we'd expect to get the same effect on the rate. And the H plus is second order again. So again, we'd expect that to multiply the rate by 4 squared. And so therefore what we're going to do is do all of those things because we have made all of those changes to the concentrations. This is something that often catches people out. We are going to multiply by 4 squared and then multiply by 4 and then multiply by 4 squared because we have done each of those changes to the concentrations. So that's what we're going to do with our calculator. We're going to take the 0.6 that we started with, multiply by 4 squared, multiply by 4, multiply by 4 squared again. And we end up with a value of 614.4. So as we said, it's had a massive effect on the rate, which is what you'd expect if you times the concentration of all of your reactants by 4. Okay, and then this is very similar to what we looked at in the last video, calculating the rate constant. So this involves rearranging the rate equation. So we need to have the rate equation in the form K equals, and as we said in the previous video, it's going to be the rate divided by all the concentrations. Okay. The only thing here is we need to be careful that we don't forget about the powers. Okay, the I minus is second order, the IO3 minus is first order, and the H plus is second order. Okay. And so again, then what we need to do is to just substitute the values in. Again, we can choose values from any of the experiments, as we discussed in the last video. But as we said a minute ago, the safest thing to do is probably to pick experiment 1 in case we've got the answers wrong for experiment 2 and 3. So I'm going to go with the values for experiment 1. So we're going to say the rate is 0.6. The I minus is 0.015, but that needs to be squared. The I3 minus is 0.01, and that's just the power of 1, that's fine. And then the H plus is 0.02, and that also needs to be squared because it's second order. And then we're just going to calculate the answer to that. And we end up with this kind of horrible looking value, which means we need to have a look at the question. It does say, give your answer to 2 significant figures. So we're going to call this, we're going to put this in standard form, because that's a kind of a horrible number. I'm going to call that 6.7 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we're going to say it's 6.7 times 10 to the power of 8. And then again, we need to work out the units as we did in the previous video. We're going to substitute in the units instead of substituting in the values. Okay, so as we said, the units of rate are moles per decimeter cubed per second, and then the units of concentration are moles per decimeter cubed. So we've got that squared, we've got it to the power of 1, and then we've got it squared again. What we can do here again is we can cancel out one set of moles per decimeter cubed from the top and the bottom. And so we can convert this and say it's seconds to minus 1 over moles per decimeter cubed in total to the power of 4 on the bottom. Then, as we discussed in the last video, if you've got something on the bottom of a fraction, it's equivalent to being to a negative power. So we can say it's seconds to minus 1 moles per decimeter cubed to the power of minus 4. And then we need to sort this out with the bracket. So we're going to call this seconds to minus 1 moles to the minus 4. And if you remember, we said we multiply these powers. So minus 3 multiplied by minus 4 is positive 12. And then the standard way of writing it is to write it with the positive 1 first. Although I should say you will still get marks for writing it in this format. But that's just kind of the standard way of doing it. Okay, finally then we have this multiple choice question. So again, they've given us the rate equation here. We can see that the H2 is first order and the NO is second order from the powers in the equation. And it says, what is the effect on the rate of reaction when the concentration of H2 is halved and the concentration of NO is doubled? Well, we said that the H2 is first order. So if its concentration is halved, we'd expect that to cause the same change with the rate. So we'd expect the rate to be halved. But then we're also changing the NO concentration, and the NO concentration has been doubled, so we're going to do another effect. And the NO is second order, so if its concentration is doubled, we'd expect the rate to be multiplied by 2 squared. So what we're going to do then is both of those things. If we times it by a half and then times it by 4, effectively what we've done is multiply the rate by 2. So therefore, the rate has been doubled, and the correct answer is C.